And it is recording now. Hello?
Hello?
Yes. Right, last time we were talking about enzyme kinetics. We're going to finish that up today and then go on to addition and elimination reactions. What we're learning in terms of enzyme kinetics is mostly so that as you're reading the literature, you can understand what's going on. We derived the steady state expression for the rate law for enzyme kinetics based on a reaction with the idea that a free enzyme and substrate associate to form an enzyme substrate complex, after which you have the step where you convert the enzyme substrate complex into the enzyme product complex, and then we are assuming that product dissociation is fast. That's not always true, but that's our simplified situation. We use the steady state approximation to get this expression, and then for reasons that become apparent later, we rearranged some terms such that in the numerator we have kcat times total enzyme concentration. Kcat is basically the turnover number. This represents basically the number of molecules per second a single enzyme can process. And it is a second order rate constant. No, that's wrong. It's a first order rate constant. We also have total enzyme concentration, substrate concentration, and then in the denominator we have substrate concentration plus some term here that is difficult to understand. It's the rate constants for things that decrease the concentration of the enzyme substrate complex versus the step that increases the concentration of the enzyme substrate complex. We call this the Michaelis-Menten constant. It has units of molar, and we'll talk about its meaning in a little bit. Some people are tempted to interpret it as dissociation between enzyme and substrate. No, that's not actually what it means. But what you can see when we look at this rate law is that there are a couple of different situations we can expect. If, for example, the substrate concentration is much larger than Km, then as we said last time, the rate law Km is less than the substrate concentration. The rate law simplifies to just having substrate in the denominator, then that would cancel out from the numerator. And then the only thing that matters for the rate of the reaction is the kcat and then the concentration of enzyme. In other words, it's independent of substrate. We would say that kcat is a first order rate constant here. Overall, remember that rates need to be in units of molar per second, concentration increase in product per second. So the molar term comes from the concentration of enzyme, and then the per second term comes from the kcat. And this is, we would say this is first order in enzyme concentration. It is zero order in substrate. And this is, we would call these saturation conditions. And what that means is that for enzyme kinetics, we expect to see a point at which adding more substrate doesn't do anything. And the reason for that is that once you've maximized, once all the enzyme substrate is bound up, once all the enzyme is bound up in the enzyme substrate complex, adding more substrate doesn't get you anywhere. And the rate determining step is just kcat. So you can think of kcat as the rate constant when you're saturated. Let's see. People have also interpreted this term in the past to be Vmax, maximum velocity, maximum rate of the reaction under a certain set of conditions. That's at this point, the only thing you can do to increase the rate is add more enzyme. All right, the second set of conditions is if Km, or if the substrate concentration is much less than Km. And under these conditions, you would expect Km to dominate in the denominator. And I said that like Dr. Doofenshmirtz. Behold, the denominator. No Phineas and Ferb fans out there? Yes? Okay, all right, sorry.
That was good.
Yes. That's the best kids shows are the ones that have a lot of sort of self-conscious humor mixed in for the adults. All right, so if Km is much greater than the substrate concentration, your rate law simplifies to this. So now you have a new rate constant. It's actually Kcat over Km. Paying attention to the units, remember that Kcat is in units of per second. Km is in units of molar. So overall, this rate constant is per molar per second, and that is a second order rate constant. And this rate depends on total enzyme concentration in molar and substrate concentration in molar. And so you can see how the units work out in the end to give us molar per second. So under this situation, yeah, you can think of this as the rate constant when your enzyme is not saturated. And if you keep enzyme concentration constant, you expect a linear dependence in substrate. So overall, the reaction is second order, but it's first order in enzyme, and it's first order in substrate. And that would be this, so here is the saturation area, here is the linear area as you increase substrate concentration. Let's see, I did tell you that Kcat is sometimes called the turnover number because it literally means how many molecules of per second or per unit time a single enzyme molecule can process. All right, now Kcat over Km can be difficult to interpret. People use it to compare how enzymes deal with different substrates because that number varies widely depending on the substrate that you have. So sometimes people call this Kcat over Km a specificity constant, but I don't know that there's anything mathematical about that. It's just because it varies widely with different kinds of substrates. All right. Questions so far? Okay, I'm gonna move that over there. Let's deal with a third situation, and that is, what if we're at a concentration where substrate concentration is the same as Km? All right, well then dP dt should equal Kcat times enzyme concentration times substrate concentration. Now Km equals the substrate concentration, so overall we end up with Kcat times total enzyme concentration divided by 2. Or Vmax divided by 2. And therefore, Km is the concentration of substrate at which we are at 50% of our maximum velocity. And another way of saying that is at which the concentration of enzyme substrate complex divided by the concentration of enzyme total equals 0.5. That is, half of enzyme is occupied as the enzyme substrate complex. All right, and some people will say, oh, well, this is how Km sort of is the constant that defines the steady state. If you have a plot like this, and this is Vmax, then if you come to half Vmax, and then intersect the plot and drop down here, this will be the Km value. All right, so in terms of just using the numbers, thinking of Km as the concentration where you're at half max velocity can be useful. All right, let's talk briefly about strategies for improving enzymes. If you're in a situation where the substrate concentration is greater than Km, then what that means is that your energy diagram is going to look like this. You have enzyme plus substrate. If you're at a concentration where substrate's greater than Km, that means most of the enzyme's going to be bound, so the enzyme substrate complex must be lower in energy. Then you have the high energy transition state, you have the enzyme product complex, which will then dissociate to be enzyme plus product. And the thing that defines the rate of the reaction is the difference in energy between the transition state and the enzyme substrate complex. Now, if your strategy binds of improving the enzyme increases the binding affinity of the enzyme for the substrate here, and similarly stabilizes the transition state, you're just going to move both of those lower in energy, and there's no catalysis. So the only way, no enhancement in catalysis, rather. If we lower the transition state and the enzyme substrate complex by similar amounts. In other words, if you want to enhance the catalysis, you have to stabilize the transition state more than the enzyme substrate complex. So your intuition about, oh, well, I need better binding affinity is true to a point, but beyond a certain point, if you lower the free energy of the enzyme substrate complex and then you lower the free energy of the transition state by a similar amount, that new activation energy is exactly the same. Okay? In contrast, if you're under a situation where the substrate concentration is lower than Km, what that means is more than 50% of your enzyme isn't occupied, and the way for that to be true is if the enzyme substrate complex is actually higher in energy than it's actually uphill to get to the enzyme substrate complex, and then here's the transition state, here's the enzyme product complex, here's the dissociated complex. Under this situation, you can, if you stabilize the enzyme substrate complex, under these conditions, the activation energy is that, difference in energy between starting materials and transition state. If you lower the free energy of the enzyme substrate complex and lower the free energy of the transition state by an identical amount, because our starting point is down here, now we have lowered the activation energy. So if we're in a situation where substrate concentration is lower than Km, if you improve, if you lower the free energy of the transition state and the enzyme substrate complex by the same amount, you're going to get an enhancement in catalysis. But that stops happening once your enzyme substrate complex is equal in energy to the starting materials. Okay, so this gives you a sense for what evolution is going to do. Beyond a certain point, there's no need to dramatically improve the affinity of the enzyme for the substrate, because that doesn't necessarily make you a better catalyst. Okay, other questions? Yeah.
So even in the second example, though, it's less dependent on the fact that your enzyme substrate is lower than energy compared to just the transition state.
Right. I mean, this doesn't matter because your starting point is lower than wherever you end up. But as soon as you lower it to this sort of break-even point, from that point on, your starting point gets lower, and so anything you do beyond that to stabilize this without stabilizing this more is not going to improve things. And evolution doesn't have any need to improve things beyond what it needs. So you'll find that in a lot of cases, enzyme KMs are pretty close to the range of physiological substrate concentration in biological systems. Yeah, others. So let's talk about so-called perfect enzymes. In water, in aqueous solution, the fastest possible reaction is diffusion controlled. So what does that mean? Well, in water, diffusion just depends on molecules bumping into each other, and so at some rate, at some stage, the ability of two molecules or an enzyme or a substrate to find each other is going to be sort of the rate determining step. Diffusion, the diffusion limit, that is how fast the maximum rate at which things can diffuse in water, is around 10 to the 8 or 10 to the 9 per molar per second. That's a second order rate constant describing the rate of two different things finding each other, and that's as fast as it can happen in water. So if your second order rate constant k cat over km, the maximum value of k cat over km is going to be, well, that's the upper limit, all right? And the closer you are to that diffusion controlled limit, the more efficient and more effective your enzyme is. Because it doesn't matter if the enzyme can process molecules faster than this, because at that point, the rate determining step will simply be substrate finding the enzyme and not the chemistry inside. So because there are two aspects to this, remember this is the second order rate constant, that is dP, which gives us the velocity of the reaction under conditions where the substrate concentration matters. That is where substrate concentration is low. Okay. Because there's two terms here, there are two ways that you could improve Kcat over Km. And let me give you some examples of two different enzymes that are basically near the diffusion controlled limit, and yet you will see that their parameters for Kcat and Km are very different. So, carbonic anhydrase. I'm not sure what that does, but it sounds like it removes water from carbonic acid or something. The Kcat over Km is 8.3 times 10 to the 7th per molar per second. So we're pushing up against that diffusion controlled limit. But if you look at what the Kcat and Km values are, Kcat is around 10 to the 5 per second. That's the turnover number. Whereas Km is around 12 millimolar. All right? So this Km value is relatively high. That means that you need 12 millimolar to have half of the enzyme total concentration bound up in substrate. That must be related to the concentration of substrate that this molecule deals with. So we could look that up. Oh, there's the K-list people. Let's see, what were we looking up? Carbonic anhydrase, substrate concentration. Go, see what it gives us. Oh, well, blah, 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 blah. Rapid interconversion of carbon dioxide and bicarbonate. So what is the concentration of bicarbonate in blood? Anybody know?
It's pretty low. I don't know what it is off the top of my head.
Okay.
I don't remember learning about it. It's pretty low.
Okay. Concentration of bicarbonate in blood. Dun, dun, dun. I just want a number. Okay, so around 24 millimolar. I mean, at least what I'm seeing there. Low bicarbonate is below 24 millimolar. High bicarbonate is above 24 millimolar. And that matches the Km value, right? So remember, if the enzyme, if evolution attempted to make the enzyme substrate complex more stable, that would have the effect of lowering the Km value beyond this, but that's not going to improve catalysis anymore, right? Because you're already up against the diffusion limit. If you lower this number too much, you know, this number is basically on the order of 10 to the minus 2. If we try to lower this by an order of magnitude, 10 to the minus 3 or 10 to the minus 4, suddenly our Kcat over Km is higher than this, which means that improvement was meaningless. It doesn't actually have an effect because now you're limited by water. All right, so that's carbonic anhydrase. Now there's another perfect, so-called perfect enzyme. That's triose phosphate isomerase. This is the one that in glycolysis isomerizes dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. And the Kcat over Km here is also wicked fast. 10 to the 8 per molar per second, again, right up against the diffusion limit. Now compare how triose phosphate isomerase does this. The kcat for this is around 6 times 10 to the third per second. So 100 times slower than carbonic anhydrase in terms of, 100 times slower in terms of turnover number, but Km is now lower. And remember that Km is the concentration of substrate at which you are at half max velocity. So a much, much lower concentration of substrate is required to saturate the enzyme substrate complex. And so between those two factors, you're again at the diffusion limit, right? So kind of cool that there are different ways to be a perfect enzyme. Anyway, anything else you want to talk about enzymes? I mean, in some ways, this is kind of dumb, because you could ask me, well, what question might you ask about those things? And I'm like, I don't know. I just want you to be aware of these things when you read the literature. All right. Well, want to talk now about addition and elimination reactions. Chapters 10 and 11 are sort of about broadly addition, elimination, substitution types of reactions. And it's sort of a whirlwind tour through the latter part of first semester OChem and all of the second semester of OChem. And some of this is just sort of gee whiz, oh, the world is more complicated than you thought. Other is kind of interesting. So we have too much material to cover, and I'm going to try to focus on stuff that's relevant. So I'm probably not going to talk about alkene bromination because it's relatively straightforward. We can talk about epoxidation, which is an addition reaction to an alkene. Classic reagent for epoxidation that's sort of commonly used is MCPBA. And this stands for metachloroperoxybenzoic acid. So here's the benzene, here's the chloro, here's the acid, and you put another OH on there, and it's this weak oxygen-oxygen bond that facilitates the oxidation reaction. So in terms of mechanism, you may have been shown this before. Sometimes people call this a butterfly mechanism. Why they do that is because they are desperate to find something to help them remember the mechanism. What happens is the pi electrons attack the sigma star of the oxygen-oxygen bond and break that bond. That bond is relatively weak. At the same time, lone pair electrons on that oxygen attack the other carbon of the alkene to prevent buildup of positive charge. We can't stop there because we'd have too many bonds to this oxygen, so we have to break the oxygen-oxygen sigma bond, and then what we're going to do reflects the fact that if we put these electrons on this oxygen as a negative charge, actually what we have is a resonance stabilized carbocation in which the negative charge can be on that oxygen. And if it is, through a 5-membered ring transition state, you can actually protonate the negatively charged oxygen, and that loses its proton, and in the end you end up with your epoxide and your benzoic acid. And where is the butterfly? Well, let's see. It's the butterfly. If you squint and tilt your head, you know, maybe that sort of looks like a butterfly. I don't know. I would have thought that people would have chosen something less peaceful and beautiful than a butterfly. Maybe it could be like the moth mechanism or something. But okay. So how do we know that this is the mechanism? Well, a lot of it is supported by kinetic isotope effects. So I'm going to try to summarize a whole bunch of sort of kinetic isotope effect and Hammett parameter types of experiments. So proton versus deuterium here on carbon B, proton versus deuterium here on carbon A, and then, you know, using MCPBA. And then let me show you the transition state that's proposed and then show you the evidence for it. So I'm going to show here is the benzene ring. Here is the position where we substitute hydrogen versus deuterium at carbon A. Here is carbon B. On carbon B, here's the position where we're substituting hydrogen versus deuterium. Here are the two bonds that are forming with oxygen. And there's, let's see, and then I believe they also used a peroxy acid, which they used hydrogen versus deuterium there as well. All right, so here is hydrogen versus deuterium. In the transition state, compared to what we've drawn above, we're breaking this bond, we're making that bond, we're breaking this bond, we're making this bond, we're breaking that bond. All right? So let's summarize the kinetic isotope effects first. The KH over KD for this proton, whoa, that's overkill, this proton is, number's really small, 0.82. That is an inverse kinetic isotope effect. We call it a secondary inverse kinetic isotope effect, and that is consistent with hybridization from a more flexible sp2 to a more rigid sp3 carbon. Okay, so that tells you that there's some amount of rehybridization at A in the transition state. Okay. If you do the same process over here, the kinetic isotope effect is basically 1, which tells you that carbon B is mostly still sp2 in the transition state, okay? Whereas carbon A is rehybridizing in the transition state. And that supports sort of an asymmetric mechanism where the oxygen is leaning towards carbon A and the bond between oxygen and carbon A is shorter and stronger than the growing bond between oxygen and carbon B. Maybe we can make that a little bit clearer. We can alter our picture based on the data by sort of sliding this over a bit. Okay, questions about that interpretation? Let's look at the kinetic isotope effect for the hydrogen on the peroxy acid. What kind of, fun quiz, what kind of kinetic isotope effect would you expect for a proton that's where a bond is breaking in the transition state? We're going to expect a primary kinetic isotope effect, and we expect it to be greater than 1. It is, but it's small. All right, and I'm not sure why it's small. The other thing we would conclude is if this carbon is still mostly sp2 in the transition state, then that would support a buildup of partial positive charge on that carbon. All right, why do you suppose that is? Why do you think we're building up positive charge here versus on A? What's different about B versus A? Yeah?
Is being able to be resonance stabilized.
Yep, resonance stabilization and of the positive charge. Now, if that's true, what do you predict if you put electron donating groups here? Should speed up the reaction, right? So when they did the Hammett analysis with the sigma values for X, they found a rho value that was negative. Now remember, the Hammett parameters were originally developed for not stabilizing a positive charge, but rather stabilizing a negative charge in the conjugate base of benzoic acid. So for the regular Hammett parameters, the more electron donating you are, the worse the deprotonation reaction gets. The fact, and that slope was positive, the fact that the slope is negative here tells you, oh, there is a buildup of positive charge in the transition state. Okay? So all of these data that you know, the kinds of experiments you can do sort of agree with this picture of the mechanism, and that when you have a substrate that has a group that can stabilize a positive charge, you're going to form that bond more slowly than that one. There actually is an example of this reaction in the app. This is epoxidation of an alkene. We're going to be here all day, so we better speed that up. Too fast, too fast. Way too slow. Dang it. Let's just go to the transition state. All right, see what's happening. Oh, shoot. In the why is it? Okay, I just don't understand. In the transition state, we'll pause there, go back to it. You can see the bonds between oxygen and carbon forming. Because either side is similarly substituted, the transition state has to have the same bond lengths here. But you can see also that, as we would predict, we're breaking in the transition state. We've already broken to a large extent this oxygen-oxygen bond, though we haven't to a large extent broken the oxygen-hydrogen bond. Anyway, a lot of different things you can get from those experiments. All right, there's some stuff we could talk about asymmetric epoxidation, but that's in your text, and if you care about it, you can look at it. I don't think I want to spend time on it. I want to now talk about addition to carbonyls and tell you just a brief story about a couple of crystallographers who learned some stuff that has sort of agreed with our MO picture of carbonyl chemistry. Whoops, that's not what we Whoa, wrong. There we go. I almost found myself saying wrong lever. Anybody know The Emperor's New Groove? Why do we even have that lever? Okay, so Hans Bergi and Jack Dunitz at the ETH in Switzerland, and some people like to pronounce that in German, so you'll hear some chemists call it the ETH. In any case, they did a survey of crystal structures, and they noticed a lot of situations in which a nucleophilic atom appeared to be close to a carbonyl group. So, for example, here is a crystal structure of methadone. Isn't that prescribed for heroin addiction sometimes? I don't know, maybe not. In any case, they noticed this nitrogen about 2.8 angstroms away from this carbonyl carbon. That's almost within bonding distance. That's maybe almost closer than van der Waals distance. And they also noticed that the angle between nitrogen, carbonyl carbon, and oxygen was around 105, which is pretty close to the tetrahedral angle. And knowing what we know about carbonyl addition and how a nucleophile adds and then you get a tetrahedral intermediate, this observation suggested to them that there might actually be a preferred pathway of approach for a nucleophile to attack a carbonyl, since this is pretty close to the geometry you're going to get in the tetrahedral intermediate. And they found a similar thing in a different molecule. This is a macrocycle, and you've got an interaction across the ring, this time even tighter, even closer, a nitrogen with a carbonyl carbon. Again, the angle is close to what you would expect for a tetrahedral intermediate. Again, suggesting the possibility of not only a semi-bonding interaction here, but also a preferred orientation for approach of a carbonyl. And I uploaded these structures into Gaussian a year or so ago and optimized them, and did something called NBO analysis, which is where you basically convert the math of MO theory into individual bonding and anti-bonding orbitals associated with each bond, and it's entirely equivalent. What I'm showing you here is the sigma out associated with the nitrogen. This would be the lone pair on the nitrogen, and this is the pi star of the carbonyl. And this area here is like a Venn diagram where they overlap, suggests that the lone pair on the nitrogen is already donating into the carbonyl. And with that orientation, because the pi star sort of angles back this way, that orientation of the nitrogen with respect to the carbon facilitates that interaction. Same thing down here with protopene. A sigma out from a nitrogen lone pair, and then the carbon-oxygen pi star. So what that suggests is that as a nucleophile approaches a carbonyl, it needs to approach via a tetrahedral trajectory, and it's going to do that because that's actually where most of the pi star is actually pointing to. So this is kind of cool because it's a physically observable geometry that you can explain based on orbitals. Right. Okay, anything you want to ask about that? Okay, that will take us through today. I intend to talk about more nucleophilic addition to carbonyls next time. We'll talk about Baldwin's rules. And then I want to talk about the E1CB mechanism, which is an elimination reaction. So we'll try to do that all next time.